Okay, so let us continue. The 100 kilogram block A is released from rest. If the masses of the pulleys and the cord are neglected, determine the speed of the 20 kilogram block B in 2 seconds. So in this problem, you have a system of pulleys connecting blocks together, and we want to determine, knowing that the speed in the system is initially released from rest, we want to determine what will be the speed of B in 2 seconds. So first, whenever you have a system of pulleys with cord, always the first step to do is to relate motion of A to motion of B. Okay? So to do this, we should determine the number of coordinates we need. So first, we have block A is attached to the center of pulley C. Therefore, they will move together. This is why we need one coordinate for A, which can be just until the center of pulley C. So I have first SA. And the second moving object is B, so I need a coordinate for B, which is SB. And always I select a reference line passing by a fixed point. So I can take this one because the center of the pulley is attached to the ceiling, so this is a fixed line. Now, after setting the coordinates, I will write the expression of the total length of my cord. So we have here, this part is a constant. We have SA. Now a constant when we go over the pulley. This is a constant. Now again SA, so it's 2SA, constant, and SB. So the equation will be 2SA plus SB equals to a constant. So 2VA plus VB equals to 0. And also I can relate accelerations. 2AA plus AB equals to 0. So until now, I found a relation between the acceleration of A and acceleration of B. But it's not enough for me because I need to determine what is AA and AB. So until now, this is a first relation between them. Since it's not enough, I should think about Newton's law in order to find another equation including acceleration. To do this, I can take free body diagrams of the different parts of my system. So here, if I look at my figure, I have first, if I consider block A is attached to pulley C through a cable. So I can consider that we have here a tension T1. And we have, of course, the weight of the block, WA. So now considering the Newton law applied on block A, since we considered that the positive coordinate is downward, we will work on this direction. So we can write that sum of forces on A equals to mass of A times acceleration of A. Now, the forces we have in the positive direction downward is plus WA minus T1 equals to MAA. So now we have obtained a new relation including AA, but also we introduced a new unknown, which is T1. Okay? So still, I need to continue because I introduced a new unknown. So until now, my unknowns are AA, AB, and T1. And I have written just two equations. Now I will move to block B. When I consider block B, the forces acting on block B are WB and the tension in this cord. Okay, so here, but can you tell me, is the tension in this cord equal to T1, or what is the relation between this tension and T1? So if I will call it T2, can I relate T1 and T2? Who can tell me how I can relate T1 and T2? What should I do?
T1 is double T2
Very good. Why?
because if we follow the pulley, then on the top of the one where T1 is located, there is T2 and T2 on right and left.
Yes. What's your name?
Steven.
Okay, Stephen. Thank you. Okay. So here, if you take this pulley as a system and you draw its free body diagram, you have the following. For pulley C, you have the T1 force acting downward. And since you did a cut at two places here, then you will have T2 here and T2. Okay? And since your pulley is massless, then you can say that sum of forces acting on this pulley is equal to 0. Okay? So sum of forces acting on the pulley is 0. So we have 2T2 minus T1 equals to 0. And this is a relation, a third equation. Okay? So this is equation 3. But I should add to my unknowns here T2 also. So I need one last equation to close my system to have 4 equations for unknown. I will obtain this relation by writing the second law of Newton for B. So now, if you write the second law of Newton for B, you have plus WB minus T2 equals to MBAB. Please pay attention in case you decided to change the positive convention in it. If you don't want to work in coordinate SB positive downward, if you want to take the upward convection, you should pay attention to put minus MBAB because AB is counted positive downward. Okay, so this is equation number 4. Now your system can be easily solved. It's a simple system. Why? Because you can do replacement. You can put instead of T1 to T2, you can put instead of AB minus 2AA, and then you will obtain 2 equations with 2 unknowns, and you can easily find your acceleration. Once you find acceleration of B by solving this system, since forces applied on the system are constant, because you have the weight of A and weight of B, which are driving motion, then you will have constant AB. And since AB is constant, you can, to find the speed after 2 seconds, you can apply the relation that VB is equal to ABT plus VB0. And since it's starting from rest, so VB0 is equal to 0. Okay, so VB equal to ABT, and that's it. Any question on this problem? So let us see together the solution. So here, for example, just they did a small calculation. You are not required to do this, but I will tell you what they are doing. They are considering if the problem is static, what will be the value of the tensions. But of course, because the system is not static, we will not have the T1 equals to WA and T2 equals to WB. Okay? And in this case, how we can know which one will be higher? It depends on the block which will, if you want govern motion, and for the weight that is much larger, it will, here for example, you have that the weight of B is 100 kilogram, while the weight of, the weight of A is 100 kilogram, while the weight of B is 20 kilogram. Okay, so here, who do you think will be able to drive motion, A or B? So the system will go, A will go down or up? You have here 100 kilogram, and just you have here 20. Okay, so it's right that here you have 2T1, but T1 will not be as large, and since here the weight is 20 kilogram. Okay, so to have just equilibrium condition, you should have a weight at A 40 kilogram. But since at A you have a weight higher than 40, so block A will move downward and will induce an upward motion of block B. Okay? So you can expect that AA will be positive, AB will be negative. And when you do the solution, you will see this. So first, as we said, the first step is to relate coordinates of in the chord. Then you can relate AA and AB. Then we can take the free body diagram of block A, block B. And of course, we can relate the tensions through the pulley. This will give us the system of equation, which will allow us to calculate AA and AB. And as expected, A is moving downward, B is moving upward. And now once you calculate AB, you can find the velocity V after 2 seconds. Okay? Now, as we have seen previously in chapter 12, we can deal with acceleration in several coordinate systems. We can work in rectangular components or Cartesian coordinates. We can work in normal tangential coordinates. So depending on the type of problem, we decide to work in which frame. Then Newton's law also can be applied in the corresponding frame. So we have already applied Newton's law in Cartesian coordinates where we have rectangular components. Now we will do the same procedure but in normal tangential coordinates. So also sum of forces equal MA, which is a vectorial relation, can be decomposed in normal tangential coordinates. And to remember, what is normal tangential coordinates? It's a frame that will follow the particle in a way that always UT, UN is the plane of motion. So UT is tangent to the path, and UN is directed towards the center of curvature. Okay. Now, when we deal with forces equations, we need to define the third direction in 3D motion. The third direction is UB. UB is defined as a vector perpendicular to the plane UN UT. Okay, so as you can see here in this figure, you have UT tangent to the path, UN directed towards the center of curvature at this location, and UB vector will be perpendicular to the plane of UN UT. And why we need UB vector? Because it will give us, equation along B will give us a third relation. It's true that since UN UT is the plane of motion, then sum of forces along B will be 0. Okay? But it's a helpful equation because, for example, if you remember in case of XY, in many cases we write sum of y equals 0 to find the normal reaction, for example. So even if no motion in B, sum of forces equals 0 will give us an additional equation to our system. Okay? So in normal tangential coordinates, the three equations to write are sum of t equals mat. This is the projection of forces along ut. Sum of n equals man is the projection of forces along un. And third, sum of b equals to 0. And of course, all we have seen in chapter 12 about normal tangential coordinates can be used. So we know by definition that at is dv by dt, and it represents the change in magnitude of velocity, while an is equal to v squared over rho, and it's due to change in velocity's direction. Now, also remember that sometimes in order to find the radius of curvature, I can, if I have y function of x, I can use the following form. okay? Because rho is required to calculate the value of A, okay? Now we will do some examples to practice on how to apply Newton law in normal tangential coordinates. We will start by a very common example, which is the Formula 1. You know that when we watch, if you watch Formula 1, you see that the rod is a little bit inclined. It's not horizontal, okay? And this inclination has a certain purpose. We will see in this problem how we can do an approximate design of theta. So the question is to determine the banking angle theta for the racetrack so that the wheels of the racing cars will not have to depend upon friction to prevent any car from sliding up or down the track. Assume the cars have negligible size, a mass m, and travel around the curve of radius rho with a speed v. So in this problem, what is the method to use? The first step is to try to draw the free body diagram of your car and to put the frame you want to work in. Why here we can think about normal tangential coordinates? Because whenever you have a curved motion, okay, especially a circle, it will be interesting to work in UNUT since you know that AN is B squared over rho. Okay, and here they are telling us that the cars are moving around radius curve of radius rho. Okay, so the radius of curvature is rho, and we want to try to express that function of rho and the parameters in the problem. Rho, v, m, maybe. Okay, so the technique is first I will consider what are the forces acting on my car. So as you can see here, you have, of course, the weight. You have the resulting normal. We will treat the car as a particle. We have the resulting normal on the car that is perpendicular to contact. So as you can see here, this is the contact line between the wheels and the race. And this contact line is inclined. Okay, so it's doing a certain angle theta with the horizontal. Now, since in the problem they said we want to determine theta to not depend on friction to have motion, this means that we don't have friction. Because in the problem they said what should be angle theta in order to not depend upon friction to move. Okay? Then no friction. The two forces acting on the car are only the weight and the normal. Now, how to put the frame? In order to put the frame, we should understand well the motion. So first here, circles you are moving on are horizontal. So imagine that you are watching the Formula car, the Formula 1. You have that, if you look from top view, you will see that it's going over a circle. So it's moving over circular tracks, and the circular tracks are in a horizontal plane. Okay, so as you can see here, each car is moving on a certain drawn line. This is a circle. It's a horizontal circle. Okay, so if you look from top, this is the top view. If you want to represent in the top view the different your frame, UNUT, UB, what do you have? This is your car, okay? Your car is here, let's say, in the top view. Then you have first UT is tangent to the path, so it's perpendicular to the radius of the circle. So if I consider this is my center of curvature here, UT is perpendicular to the radius tangent to the circle. UN is always directed towards the center of curvature. And here, since it's a top view, it's a horizontal plane, then UB will be along the vertical perpendicular to UN UT. So I can just represent it by a point and a circle axis. So these are my unit vectors, U, T, U, and U. Okay. Now, I can also present my forces in this view, but we will see that the profile view will be much clearer. Okay, so here what do I have? I have the weight. The weight can be represented by an axe like this and a circle, so it's perpendicular to the screen, towards the screen. And you have the normal. Now the normal is not easily represented here because it has two components. Okay, we will see together that it has a component along UN and a component along UB. So in order to better see the forces, we will do a profile view, because as you can see here in the profile views, your forces are clearer. So in the profile view, this is your normal, this is your weight. Okay, but I want to represent now UN, UT, UB on this figure. Okay, first, how will be UT on this figure in the profile view? So if you just represent the particle, now profile. In the profile view, I will see my car. Okay, now how will be UT? Imagine that you are looking at the car and...
Hi, doctor.
Hello.
I'm sorry I'm late, but I was doing registration for my classes in summer.
No, it's fine. It's fine.
Thank you.
Okay. So you have here UT. UT will be towards you. Okay. So if you imagine that your car is rotating, and then UT will point towards you. You have UN. The center of your circle is somewhere here. So UN will be like this. So you can present UN directed toward O. So let's say this is O here. And concerning UB, UB is vertical. Okay, so this will be UB. And now you can put your forces on your free body diagram and project them. So your forces are the weight, W, and the normal reaction, N. So concerning to be able to do your projection, you should know what is the angle between N and your vectors. So here, for example, as you can see in the figure, N is perpendicular to the inclined line, okay? And the weight is perpendicular to the horizontal. So the angle between the incline and the horizontal will be equal to the angle between N and UB, okay? So this angle here is that. Now, once I have my free body diagram with the vectors UN, UT, UV, I can easily now apply the second law of Newton. Okay? Any question on how we put the unit vectors? Is it clear how we put UN, UT, UV, and how we represented the free body diagram? This is the most important step in the problem. Once done, it becomes very easy to continue. Okay? So, you can see here again the representation of the free body diagram. Now let us apply together the three equations. So first you have sum of t equals MAT. Do you have any force along UT here? If you look at your figure, UT is perpendicular to the screen, and forces N and W are in plane UN, UB. So they don't have any projection along UT. So you can just say that sum of t equals 0, and this will give you that V is constant in this case. No change in speed. So V is constant. This is the first relation. Now, if I project on UN, I will write that sum of N equals to MAN. You can see that the weight is only along UB, so no projection along UN. You only have the projection of the normal force. So this is, you have N sine theta on un. Okay, so if I project, I have n sine theta equals to an is v square over rho, so you can replace an by its value, so m times v square over rho. Okay, so this is equation 1, this is equation 2. As you can see here, you have two unknowns, n and theta, and we want to try to express them function of our variables, mv rho. Okay, now I will write the third relation. The third relation is sum of b equals to 0. So if I project now along UB, I have the projection of the normal, which is positive upward, and the projection is n cosine theta, while the weight is vertical downward. So I get that plus n cosine theta minus w, so minus mg, equals to 0. So this is equation number 3. And now, if you look at equations 2, 3, you have two equations, two unknowns. The unknowns are n and theta. Okay? So how we can eliminate n? If you write from equation 1, you have n sine theta. Equation 2 gives you that n cosine theta is equal to mg. So if you divide 2 by 3, you will obtain the expression of tangent of theta. Okay, so now dividing 2 by 3, 2 over 3, n sine theta over n cosine theta, n will be simplified. So you will have tangent of theta is equal to, you will see that m will be simplified, so you will get v square over rho g, and therefore theta is given by tangent minus 1 v square over rho g. Okay, so you express theta function of the parameters in your problem, the velocity v and the radius of curvature and g. Any question on this problem? So we can see together here the solution. So first, as we said, we did the projection on un and ub, and we obtained two equations. Now, by eliminating n between the two, we get that theta is tangent minus 1 of v square over rho g. Another problem, as practiced on UNUT frame, the design of the ski requires knowing the type of forces that will be exerted on the skier and his approximate trajectory. In the case as shown, determine the normal force and acceleration on the 600 Newton skier the instant he arrives at the end of jump A, where his velocity is 9 meters per second. So let us see the figure here. In this problem, we have a skier moving on a path of equation y equals to 1 over 60 x squared minus 15. And we want to determine what is the normal force at A and what is its acceleration at A. So here, in such problem, how we should think? It's true that we have a y and x. Okay, so if you think to use your equation in rectangular components, you should have additional information because you don't know anything about acceleration. So you have ax and ay, two unknowns. While if you use normal tangential coordinates, then an can be written as v squared over rho, and v is given at a, and rho you can find it from the equation of your path. This is why always, if you know the equation of your motion, then it's better to use UNUT, because in UNUT, knowing the radius of curvature will directly give you AN, which will reduce the number of unknowns. While if you write your system in X and Y, you will have, instead of one unknown, which is AT, you will have AX, AY, which will complicate the analysis. Okay? So always, when you have circular motion, or when you have Y function of X, think about using normal tangential coordinates. إذا you know, for example, information along on AX, AY. And for example, if I give you X function of time and Y function of time, then it will be easier to work in rectangular components. You just derive, you find Vx, Vy, then Ax, Ay, and you project on X and Y directions. But in case you don't have any other information than the path of motion, the equation of the path, then you cannot find what is Ax and Ay. The number of your unknowns will be higher than your number of equations. This is why it will be better to work in a frame in which you have something known as UNUT, because in UNUT, you can say that AN is B squared over rho. And in this problem, they told us that when we reach A, velocity at A is given. So velocity at A is equal to 9. Since it's given, then all I need to do is to find rho at A to be able to calculate the normal acceleration at A. Okay, so now the idea is to say that I will work in normal tangential coordinates. At point A, UT is tangent to the path, and since I am, if you want, at x equals 0, I will have a horizontal tangent at this location. Then UT is horizontal, and UN is perpendicular to UT, directed towards the center of curvature. Why here? From the figure, you can see that the concavity is upward, so UN is up. Or if you want, if it's not clear in the figure, all you have to do is to do the second derivative. If you have a positive second derivative at A, this means that UN is upward. If you have a negative second derivative, this means that UN will be down. So here, the function is easy. If you do the first derivative, you have that dy over dx is 2x over 60, so it's x over 30. And therefore, if I do the second derivative will be 1 over 30, okay, which is positive. Since the second derivative is positive, at any point, my concavity is upward, and then I can say that UN will be also up, okay? So this is positive, equal to 1 over 30. And now, at any position, so for example, if they ask you about the skier at this location, for example, you have UT downward, tangent to the path, and UN will be perpendicular to UT and pointing upward, okay? Now, we are in particular interested in point A, so let us draw the free body diagram at A. The forces acting on the skier are its weight and the normal reaction, okay? Now, at this location, if I project my forces, the first relation will give me sum of t equals MAT. Since no forces along UT, then sum of t equals 0. This means that at this particular location, AT at point A is 0. Why we have this? Because just at this location, the weight and the normal are collinear, and we don't have forces along UT. Now, concerning the second equation, we want to project on UN. So sum of n equals to MAN. If you look at your figure, you have NA pointing towards UN positive, so it's plus n minus W equals to MAN, and we know that AN is V squared over rho. The velocity at A is given, it's 9, it's given in the problem. Now we still just need to determine what is the rho at point A. So to find rho at A, we will use the formula developed in previous chapter. If we know y function of x, we can use the formula of rho to get function of dy dx and second derivative with respect to x at point A. So at point A, x is 0. This means that dy by dx is 0. And the second derivative is 1 over 30. So now all we have to do is to replace in the expression of rho. So as you can see here, we have the expressions for the first and second derivative. We find what is the value of rho at A, and then we can replace rho in the first equation, sum of n equals man, to get the value of the normal. Now, they asked for the normal and they asked for the acceleration. You know that the acceleration is divided in curved motion into two components. But at A, since at is 0, then the acceleration at A will be just equal to an. And we have already calculated rho, so we can simply say that an is d squared over rho. And therefore, the acceleration at A is upward equal to 2.7. Okay? Any question on this? Okay. Now, for example, this problem can be a little bit harder. So if they gave you a position that is more critical, for example, here, a certain point here, okay? Then what will happen? Everything will change here because the weight and the normal will not be anymore collinear. So you will have projection along UT and you will have projection along 2n. So let us consider a more complex case. So this is UT. Look, I will open a new session because this one will end soon, okay? And we'll continue in the second session.